So the key to understanding what happens to Earth when you get a coronal mass ejection that hits, that's space weather, and it's a field of study. In fact, we call it space physics, which looks at the physics of how the sun and the Earth interact. The key is Earth's magnetic field. So Earth's magnetic field surrounding Earth, and that magnetic field protects us from things out in deep space. So the Earth's magnetic field out here is there protecting us from charged particles flying through space. But when the sun has a coronal mass ejection, this black charged particles hits the Earth's magnetic field. The Earth's magnetic field directs some things around, compresses, pushes on the Earth's magnetic field. So the magnetic field lines get pushed inwards a little bit, and then what happens is particles leak into the magnetic field, magnetosphere of the Earth. That happens anyway, and there's actually a whole bunch of particles that are trapped orbiting around the Earth in high energy particles orbiting on the Earth. If you get blasted by these high energy particles, that looks like radiation. In fact, this was discovered by Irwin Van Allen during the very first American space mission, the Explorer 1 spacecraft. And so these are called the Van Allen radiation belts. And what happens, though, is that during this event in which the sun's coronal mass ejection is interfering with the Earth's magnetic field, we call it a geomagnetic storm. The Earth's magnetic field bends a little bit, it fluctuates quite a bit. And so as it fluctuates a little bit, then what happens is you get magnetic reconnection that adds extra energy to these particles. Some of them go flying around out here, some go raining down into the atmosphere. So what happens is we get radiation events. It's particularly bad if you're actually near, because if you look at the magnetic field here, you notice that these things kind of bend around in here and go in, and so that's where you get it worse is the north and south poles, that north and south magnetic poles, and so you get. But it can be anywhere on Earth that these things are slamming into the atmosphere. So you happen to be high in the atmosphere, and again, the deeper you are in the atmosphere, the less of it makes it down to the ground. So the higher you are, the more radiation exposure you get. During one of these events, if you're in an aircraft, you can actually get exposed to very large amounts of radiation. In some cases, somewhat dangerous amounts of radiation during a major event of this sort. And likewise, these things, all these particles hitting the atmosphere, they can also create problems in the upper atmosphere. We have a layer of the atmosphere that's somewhat ionized called the ionosphere. The ionosphere can either be overcharged and then reflect radio waves, so that would mean that, for example, you would have no satellite communication. So during a major event of this sort back in the early part of the century, about 2003 or so, for several hours one afternoon, there was no satellite communication. Well, that means your network programs that were being broadcast weren't available. It also meant that your GPS didn't work for a few hours one afternoon. It meant that some long-distance phone calls weren't going through if they were going through satellite. It also meant a lot of bank problems were having. ATMs, things like that connected wirelessly. I mean, they used wires, that's one thing, but a lot of them were using satellite links. That was offline. And so a great many things were suddenly offline that we kind of depend on. And so that was a huge deal right there. During one of these events back even years earlier in California, for example, it was reflecting back down into California and amplifying signals. The kind of signals that were amplified were actually about the signals that were used for garage door openers. Now, there's only so many different combinations for garage door openers, so what would happen is someone would press their garage door opener button, and normally it has a certain range, and the likelihood of there being two garage doors with that same code right around there is pretty slim. But when this was happening, you'd press that, and that signal would be amplified all over the east, or all over the west coast. And so, you'd press your button, and garage doors, from Seattle down to Los Angeles were opening and closing randomly, and of course, that's a security issue. The other thing that happened back in the 90s is that it knocked out communication that was used by a lot of police departments. California Highway Patrol had no access to dispatch for a while, so the officers had to drive down the highway. They could not call for help if they got into trouble, and they'd drive for a while and they'd stop. And this is, you didn't have cell phones. They weren't working either, and there weren't as many in those days, and so they had to stop and use a payphone and call the dispatch to see, if they had to respond to anything. And so so this was a big geomagnetic storm. It would impact navigation if you use radio navigation beacons. That actually happened also a number of years ago, and ships were using radio navigation beacons. They didn't work, and so all this happened. In addition to that, you had these particles that were up here slamming to the atmosphere. When that happens, it knocks electrons off of the atoms that are already in the atmosphere. When those atoms grab the electrons back, then they give off light. And when that light is visible from the ground, you look up and you see this glowing in the sky. Depending on which atoms it is, nitrogen or oxygen, whatever, you get kind of a reddish glow or a greenish glow, and we call that the aurora. The aurora borealis is the one in the northern hemisphere, and the aurora australis is the aurora in the southern hemisphere. And so, seen from above, the aurora would look like a big oval up here. In fact, we call it the auroral oval. And seen from below, you see these patterns here in the sky, reds and orange and yellows and so forth, mainly reds and greens though. Now, the more active the geomagnetic storm is, and that's what we call all of this, geomagnetic storm. This is the effect of that coronal mass ejection. It's fluctuating Earth's magnetic field that produces electrical currents in places you don't normally get electrical currents. Anything that's long pieces of metal get electrical currents in them. It would also create these radio blackout conditions. It also creates the aurora. It also creates radiation events and so forth. In fact, because of the aurora here, this is charged particles slamming the atmosphere. When this is happening, when you have a particularly vivid aurora, they actually issue aviation warnings. You're not supposed to fly under this thing if you can avoid it because of the radiation exposure. And so, but when you get a particularly big solar storm and the geomagnetic storm associated with that is particularly large, then what happens is the auroral oval moves farther south. Now, I've actually seen the aurora visible from Texas as during a major geomagnetic storm. If you're outdoors at night, near solar maximum, you can sometimes see this. And I've seen it. The first time I saw it, it was like just kind of this weird sort of thing. I wasn't sure what was happening. It was like, it looks kind of reddish and then off to the north. I thought someone's taillights, from a car that was like just over a tree line. And then all of a sudden it erupted into little spikes going up and down. And it was one of these spike form auroras. There was another time that there was really dry out and they'd been having some wildfires, and I saw the sky getting kind of bright up to the north, and I was thinking, oh my gosh, there's a fire up there. And then all of a sudden it's turned into these ripple sort of things, curtain type sort of thing. So I've seen the aurora several times here from Texas. It's not very common, but it can happen when you have a particularly powerful geomagnetic